Imagine asking your computer, hey, how many penguins are in this video? And it actually gives you the right answer. No training, no manual tagging, just point and count. That's exactly what this new paper sets out to do. It's called COUNTVID, and it tackles a surprisingly tricky problem. Counting any object in any video, even if the object disappears, reappears, or blends into a crowd. The system uses a mix of text or image prompts, a smart counting model, and a tracker that can follow objects across time without losing track or double counting. And to top it off, they built a whole new benchmark data set, Video Count, featuring penguins, fish, humans, and even metal crystals in X-ray footage. Yup, the science goes deep. So how does COUNTVID actually pull this off? Let's zoom into the stages, the models, and the clever tricks behind this open-world video counter.
All right, let's kick things off by examining the intriguing visual at the top. Imagine you're watching a video of fish swimming in a pond. The model we're discussing, COUNTVID, labels each fish with unique colors and numbers. This clever trick helps track each fish without missing any, even when they swim behind one another. Below these frames, there's a graph showing the number of fish over time, visually demonstrating the model's ability to keep count as the video plays. Moving on to the abstract, it introduces a fascinating challenge: counting objects in an open-world setting. You might start with a simple description like fish, and need to count all those fish in a video. Sounds straightforward, right? But it gets tricky when the scene becomes crowded, and objects overlap or reappear. COUNTVID tackles this by combining image-based counting with video segmentation and tracking to automate the process. They even developed a dataset called Video Count to test their model. It's sourced from various places, including tracking datasets and unique videos of penguins or X-rays of metal alloys. This dataset shows that COUNTVID isn't just theoretical, it outperforms other strong methods in real tests. Everything is available online, inviting anyone interested to explore further or even build upon it. Now let's dive into the challenges of counting objects in videos. Imagine trying to track the same fish across multiple video frames. You definitely don't want to count the same fish twice, right? Here, the problem of instance identification comes into play. It involves deciding if a fish in one frame is the same as a fish in another. It's particularly tricky with objects like insects or birds that look so similar. Surprisingly, automated counting in videos hasn't been explored much, unlike counting people. The need for automated video counting is massive. Conservationists, for instance, spend ages counting animals via drones. Materials, scientists, and epidemiologists face similar tasks. An open-world approach like COUNTVID could really change the game, eliminating manual counting and speeding up research. COUNTVID is designed specifically for this. It takes a video and a prompt, either text or images, and counts the unique objects in the video. It builds on advances in image counting and video tracking, using sophisticated techniques to handle crowded scenes. It leverages the latest image counters and video models to count accurately without extra training or manual input. This innovation could revolutionize how researchers across fields approach video data, making insights easier and faster to achieve. Next up, let's talk about the innovative Video Count dataset. It's crafted to evaluate video object counting models and contains two types of benchmarks. First, it enhances existing tracking datasets by adding more annotations, ensuring every object is counted. Second, it introduces fresh scientific footage, like penguins in the wild and X-ray images, to test models in diverse real-world scenarios. The paper makes 4 key contributions. First, it outlines the novel task of counting objects in open-world videos. Second, it presents COUNTVID, a model tailored for this task. COUNTVID combines open vocabulary image counting with class-agnostic segmentation and tracking models. Third, it extends COUNTGD, focusing on outputting bounding boxes for counting, and introduces an automated method to remove false tracks. Lastly, it offers Video Count as a comprehensive testing ground for video counting algorithms. When it comes to related work, the focus has mostly been on images, where foundational models specify categories using text. COUNTGED stands out for handling both text and visual inputs, adapting to new classes without human intervention. In videos, existing open-world trackers fall short, especially in cluttered environments. The limitations of these trackers highlight why COUNTVID-driven's approach is so crucial. Let's explore how COUNTVID works. It uses a clever 3-stage process for counting objects in videos. In the first stage, the model takes text descriptions and image examples to create box prompts for each video frame. This helps identify where objects might be, and a segmentation model then turns these prompts into object masks. Think of it as highlighting areas of interest in each frame. In the second stage, the model addresses potential errors from stage 1. It uses a temporal filter over a sequence of frames, helping to remove any false positives. Objects incorrectly identified in a single frame, but not consistently present across multiple frames. It's like double-checking your work for accuracy. Finally, in stage 3, the model spreads the object masks from stage 2 across all frames. This step is crucial for spotting new objects that might appear as the video progresses. By doing this, COUNTVID ensures that the final count of objects is as accurate as possible. Overall, this structured approach allows COUNTVID to provide both frame-level and global object counts, making it a robust tool for open-world object counting. The model's ability to adapt to text and image prompts makes it versatile for various applications, from wildlife monitoring to industrial inspections. Now let's see how COUNTVID processes videos over the long term. In stage 3, the model uses a segmentation and tracking approach to manage the entire video, ensuring every object is tracked accurately. It compares existing object masks over time to spot new objects. If a mask doesn't overlap with any from previous frames, it's marked as new. This method allows COUNTVID to adjust for objects appearing or disappearing due to movement or occlusion, creating a comprehensive count by the end. For implementation, COUNTGD handles counting and detection, while SAM 2.1 manages tracking. The idea is to use box prompts to guide the segmentation model, ensuring accurate mask creation, especially in dense scenes with overlapping objects. COUNTGD is designed to generate box prompts effectively. Unlike other models that only use points, COUNTGD focuses on providing clear boundaries for objects, which is essential for precise counting. This approach resolves ambiguity and enhances accuracy by defining object regions clearly. In a nutshell, COUNTVID, supported by COUNTGD, offers a robust framework for tackling complex video counting tasks. It combines flexibility and precision, adapting to various input types, and ensuring even crowded scenes are handled with ease. This makes it a powerful tool for real-world applications where accurate counting is critical. Let's unpack the details of the video count dataset. This dataset is a game-changer for testing object counting in videos, addressing gaps in existing datasets. Look at Table 1 here, which presents 3 benchmarks: TAO count, MOT20 count, and science count. Each offers unique challenges, from varying object numbers to diverse video lengths. This variety ensures models like COUNTVID can adapt to a broad range of real-world scenarios. The dataset's strength lies in its diversity. TAO count and MOT20 count expand on existing tracking datasets, while science count introduces new footage like penguin monitoring and crystallization processes. This mix tests the model's ability to handle everything from sparse scenes to dense, complex environments. The page also touches on the technical aspects of COUNTGD, which is integral to COUNTVID. It uses advanced loss functions to fine-tune box predictions, ensuring accuracy. This allows COUNTVID to provide precise object boundaries, crucial for effective segmentation and counting. In essence, video count is designed to push the limits of open-world object counting. It challenges models with unique and varied data, ensuring they can handle different real-world applications. This makes it an invaluable resource for advancing research in video analysis. Let's dive into the evaluation of COUNTVID using the video count dataset. Look at Figure 3 here to see how COUNTVID tackles different challenges, like dense and deforming objects, showcasing its robustness in real-world scenarios. For datasets and metrics, the page discusses using FSCD 147 to evaluate counting and detection accuracy. This dataset includes bounding boxes for objects, and performance is measured using mean average precision at various thresholds. These metrics help assess how well the model identifies and counts objects in complex scenes. When it comes to video evaluations, metrics like mean absolute error and root mean squared error are employed. Adapted from image processing to fit video tasks, they measure the accuracy of object counting by comparing predicted counts against actual counts. The focus is on maintaining the uniqueness of object identities across frames, ensuring no double counting or misidentification occurs. Overall, this page highlights the rigorous testing phase COUNTVID undergoes to prove its effectiveness. By using comprehensive datasets and precise metrics, the model's ability to handle diverse and challenging video environments is thoroughly assessed, showcasing its potential in dynamic real-world applications. On this page, let's talk about the power of the temporal filter in reducing errors during object counting. Check out Table 3 here, which shows its impact on the TAO count dataset. When using text prompts, the temporal filter cuts errors by more than half, demonstrating its effectiveness in refining object count accuracy. The page also examines different methods and their performance on the FSCD 147 dataset. It compares counting and detection accuracies using various prompts, such as text, exemplars, or both. COUNTVID box emerges as a strong performer, especially when using both exemplars and text. However, its performance can vary based on the type of prompt used. The evaluation emphasizes that models like COUNTVID box need to be versatile, handling diverse scenarios, whether it's dense overlapping objects or sparse scenes. While it's a strong all-rounder, specific settings might demand other models. For instance, in scenarios where detailed location info is crucial, certain models might perform better. Overall, this page underscores the importance of adaptable models and the role of techniques like temporal filtering in enhancing accuracy. By focusing on these nuances, COUNTVID can effectively tackle the complexities of video object counting in varied environments. Finally, let's dive into the performance of COUNTVID on the ScienceCount dataset. Take a look at Table 5 to see how different setups influence accuracy. The results highlight how COUNTVID, when paired with COUNTGDBox and SAM 2.1, achieves superior counting precision compared to baseline models like MASA and ByteTrack. Using both text and exemplar prompts seems to enhance accuracy, suggesting more contextual information helps in counting tasks. The page also compares two strong baselines. The first uses MASA with grounding DINO, and the second combines ByteTrack with COUNTGDBox. COUNTVID significantly outperforms these setups, especially with both text and exemplars, demonstrating its versatility across diverse video conditions. Interestingly, the table shows that while GECO works well for images, COUNTGDBox remains more effective for video counting. SAM 2.1 excels in handling complex environments, particularly in the exemplar-only setting for crystals, but is slightly less effective for penguins. Overall, this page reinforces COUNTVID's robustness and adaptability, demonstrating its impressive capabilities in various configurations. By effectively leveraging detailed prompts, COUNTVID sets a new standard for accuracy in video object counting. Thanks for joining us today. Happy exploring together!